All right, so let's write down, I'll keep our reference triangles handy, and actually, you know what? Let's use degrees today. I think most of the examples we're going to do are in degrees. So 45 degrees, of course, and then 30 degrees and 60 degrees are our reference triangles. This diagram, we probably won't need too much. Since the law of sines and cosines, take calculus. Law of sines and cosines primarily involves solving for values and side lengths of a triangle. So since we're given an absolute triangle and we're not given some sort of relative positioning in a reference frame, we don't have to worry about pluses and minuses too much. For pretty much everything, things will be positive. Let me think. So I don't think we'll need anything else. Any of the cofunction identities or the Pythagorean identities or anything like that. So let's just keep this as our reference sheet with our values here of our two reference triangles. And then the next thing we may want to start adding to this and writing down are the law of cosines and sines. So we'll start off with the law of sines. So in these situations, we're going to have a triangle, and the way we typically label our triangle is we'll use capital letters for the vertices, so A, B, and C, and we use those for an angle. So if I just say find capital A, it means find angle A. Then across from the angle, or across from that vertex, there's a side, and we'll use lowercase letters to dictate the side lengths. And we always correspond the lowercase and capital letters across from each other. So that should be a capital C. That's just a little c there. And what does the law of sines say? Law of sines says that the relative value of the sine of an angle to its opposite side is constant. So mathematically, that means if I take the sine of an angle and divide it by the opposite side length, this is the relative values of those, then that is going to be the same for all corresponding ratios of the triangle, meaning that sine A over A is equal to sine of angle B over B is equal to sine of angle C over C. So things that you can use the law of sines for. So hopefully you're kind of familiar with this notation way back, either in high school somewhere where you took geometry. You did basic, hopefully, triangles and congruent triangles and saw this somewhere. This means angle, angle, side. So if I'm given two angles and a side where the side is not in between the two angles, it's going to work well. And actually, I guess we could include angle, side, angle in that situation as well. Anytime you're given two angles, law of sines is going to work well. Because what we're going to do with law of sines is essentially just pick out one of these equations. And we are going to relate, if we can relate the sine of two different angles, we can automatically, well, if I'm given two angles, we can automatically find the third, and then whatever the side is used, we can use in one part of the equation. Then we're left with one unknown, and we can solve for the remaining values. If you're given two sides, however, you need to be given two sides and not the included angle. So we call the side angle. So something like if I give you value C, value A, and then angle C, we can use the law of sines. Law of sines is going to be hard to use if you're given side, angle, side. We'll use the law of cosines for that. So let's see a couple of examples. So let's say we were given that A is 45 degrees, B is 60 degrees, and side B is 8. And we are asked simply to find A. So we recognize we're given two angles and a side. And when we look, I am given angle A, angle B, and then side B. So two angles and a side. I can find the third angle if I want to. However, what side are we interested in finding? We're finding side A, which is opposite that angle. So I'm given this guy, and this guy, and it'll fit nicely in with the law of sines to find side length A. So we'll just plug it into our formula. Sine 45 degrees divided by A, which we don't know, is equal to sine B over B. Sine of 60 degrees over, and B was 8. So I'm just plugging in the values into that equation for the law of sines. And now we just solve for A. So let's go ahead and compute that out. Sine of 45 degrees, if you look at your reference triangles there, is 1 over square root of 2. Sine of 60 degrees is square root of 3 over 2. And our B was still 8. Now we just solve for A. So if you want, you can cross multiply. That's an easy way to do it for you. So we'll have 8 times 1 over square root of 2 equals square root of 3 halves times A. Then we got to divide by square root of 3 over 2 or multiply by 2 over square root of 3. So we will get 8 over square root of 2 times 2 over square root of 3 equals A. How do we simplify that? Well, there's some equivalent expressions, especially since we're not requiring that we rationalize the denominator. We could divide the 2 and 2 and put the square root of 2 on top if we wanted to, or we could simply combine the square roots in the denominator. So we could write this as 16 over square root of 6 is one valid answer if we just multiplied straight across. We could write it as 8 square root of 2 over square root of 3 if we wanted to. Since 2 divided by square root of 2 is square root of 2. So that'll give us that square root of 2 in the numerator, and then 8 over square root of 3 remains. And of course, this one, if you wanted to even write differently, you could write as 8 times square root of 2/3. All of those are equivalent. All of those are equivalently simplified as well. So all should be accepted. Other examples. Let's do A is 135 degrees. B is 15 degrees. C is 12, little c. And now we want to find A. Oops, side length A. So now what are we given? We are given angle A, angle B, and side length C. So I'm given angle A, angle B, and side length C. So we are given in this angle side angle situation. Angle side angle isn't ideal, but it's still doable with the law of sines. Since the law of sines relates an angle with its opposite side, and the only side we're given is side C, we really want to be able to find angle C. And luckily, since we're given the other two angles, we can do that first. So one small step before we use the law of sines, we can say that C is 180 minus 135 plus 15. Of course, all those are in degrees. And 135 and 15 is 150. So our C is 30 degrees. Now that we're given C and side length C, we can set up our ratios with the law of sines. So this is going to say sine of A divided by A. So since we want to find A, we're going to have that part in our equation. Sine of angle A divided by side length A is going to be the sine of C over side length C. And again, we just solve. So sometimes the angles you will not be able to compute by hand. So fair warning, only use calculators on homeworks, WebAssign, and written homework, sometimes the TTs. Never use calculators on tests or quizzes. Question quizzes, all the angles we should be able to compute by hand. So that's why I'm trying to use angles that we are computing by hand. However, if you can't, I'll go about the problem solving process and we'll see how the answers should look. So I just multiplied the A over, then we can multiply by 12, divide by sine of 30. And that would be a good answer. If I can't compute the angles, we would leave it like that. If it were, some funky value, sine of 59 degrees or something like that. But since we can compute those values, we can go ahead and compute it out. Let's see what we got. So 12, what is sine of 135 degrees? So 135 degrees, how big is that? We need a little bit of this. It's over in the second quadrant, and it's got a 45-degree reference angle. So it's 90 plus 45. So that's our 135 degrees. And so since the reference angle is 45 degrees, sine of that is going to give me 1 over square root of 2. Sine of 30 degrees, go ahead and look at our reference sheet, we get 1/2. And so let's simplify that. That's going to be 12 over square root of 2 times the reciprocal of the denominator. And again, 2 divided by square root of 2 is just square root of 2. So we'll get 12 square root of 2 is side length A. Questions so far? Okay, let's do one more example. There is one problem that can come about with law of sines, and that's when we're given these side-side angles. Let's go ahead and redraw that triangle real quick. So let's say we're given A is 30 degrees. Little a is 20. B is 30. And we want to find angle B. So the problem that can come about is that if I'm just given side A and side B that are fixed lengths, then we don't know side C. And so we could have one solution that looks like this, but we could also have another solution where angle A is still 30 degrees, B is the same length, but side length A, instead of coming out here, we can actually swing it to the inside, and it gives us two possible solutions. So this could be A, or this could be A, which is going to change how big angle B is. Let's see what happens. So let's go ahead and try to set this up. We have sine 30 degrees divided by A, which was 20, is equal to sine of B over 30. We got to solve for that angle, and so we'll get sine of B is equal to 30 over 20, sine of 30 degrees. So sine of angle B is 3/2 times sine of 30 degrees, again, was 1/2. And so we get 3/4. So this is a slightly problematic situation because we need to solve this trig equation, but you got to be careful with using inverse trig functions. So why do we got to be careful in this situation? Because this is a trig equation. The ratio is positive, and where is sine positive? In the first two quadrants, quadrants 1 and quadrants 2, meaning any angle between 0 and 180 degrees will have a positive sine ratio. And if it has a positive sine ratio, that's going to, or if we're given a positive sine ratio, then an angle can correspond to any angle within those two quadrants. And since we're using real world triangles, any of these angles are valid between 0 and 180 degrees, which is why we're going to end up with two solutions, one with a first quadrant angle and another one with a second quadrant angle. So if we tried to use inverse trig, we don't have a reference triangle for sine equaling 3/4. So one solution is going to be arcsine of 3/4. However, where is this quadrant? Because arcsine spits out in quadrants 4 and 1, this is going to spit out a quadrant 1 value. We also need to find the quadrant 2 value. So how do we find the value in quadrant 2? Well, since this one is in quadrant 1, this necessarily gives us the reference angle. So if I need an angle in quadrant 2 with that same reference angle, we do 180 minus that. and this will be in quadrant 2. Let's compute those real quick just to get an approximation for the value. So arc sine of 3/4 in degrees is going to be about 48.59. I should use squiggles here, approximately. So again, only use our computational devices on homeworks and Teamwork Tuesdays. And in this case, now we would have 180 minus 48.59. And so we get see, what is that? So 31.41 degrees, 131. Any questions on that? So again, if we were to try to draw this, let's see if we can try to draw it to scale. We have one solution where one angle is 130 degrees, where our A is 30 degrees, 131. Our B was 30, and our A was 20. And then our other solution would have been something like that. I guess it would have been smaller since it would have been 48 degrees. So something like 48 degrees here. So again, we can kind of have free range of swinging this side. If we imagine this as a fixed bar and just swing it outward and see where it hits this line that C is going to lie on, it'll hit twice while keeping that side length fixed, this side length fixed, and that angle fixed. And it gives us two separate solutions. Okay, so let's see, how much time do we have? Let's state the law of cosines real quick. I'm not going to do any examples since you'll have all day tomorrow to practice it with Ali and on the Teamwork Tuesday. The law of cosines says that it's essentially the Pythagorean theorem. So let's actually write that out. So it's going to be a squared is equal to b squared plus c squared is where you want to start. However, if it's not a right triangle, we need a correction term. So you can think about it that way. Think about it like the Pythagorean theorem with a correction term. And the correction is going to be minus 2 times BC times the cosine of angle A. So Pythagorean theorem, a squared equals b squared plus c squared, or you can permute all the variables. And then the correction term is always minus the two corresponding sides on the right-hand equation, 2 times b times c times the cosine of the included angle. So you kind of want to think about it as given C, B, and A, and then the angle between B and C is what goes here. And we can permute all of these variables in whichever way we want. So you could have B squared equals A squared plus C squared minus 2AC. Cosine of angle B. C squared equals A squared plus B squared minus 2AB. Cosine of angle C. And so the nice thing about the law of cosines is that it works for any triangle, not necessarily right triangles. There's not necessarily a dictated hypotenuse, so to speak. And so you can essentially set up the same equation depending on which pieces of information you're given. So I'll just make a note useful for side, 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 and side angle side. If you're given two angles, you basically have to use law of sines. But anytime you're given two sides, as long as the angle is included in between the two sides, so if I'm given side B, angle A, and side C, we can use law of cosines. Or if I'm given three sides, we can use the law of cosines to solve for the rest of it. Any questions?